Tracking of catheters under fluoroscopy has been achieved by placing radiopaque marker bands at the catheter's tip, as shown here. This provides an estimate of position of the catheter tip, however neglects to track the orientation in a planar image, as evidenced by the simulation, where the only indication of rotation comes from the moving coordinate frames. When navigating steerable or robotic catheters, it is critical to track this orientation to safely manipulate the catheter. Existing works aiming to track catheters fall into sensor-based and image-based approaches. Electromagnetic tracking requires coils placed in the catheter, which provides complete pose information but lacks shape information and is hard to miniaturize for thin-walled catheters. Optical fiber approaches such as fiber Bragg grating sensors can provide shape information but are expensive and sensitive to thermal effects. Many works have reported segmentations of catheters as a spline, assuming the material is radiopaque, but does not capture rotation along the backbone. As previously mentioned, segmentation of marker bands captures position information at discrete locations, but does not inform shape or orientation. Our approach builds off of existing works by using existing clinical imaging to capture complete shape and pose information without relying on additional sensing modalities. We achieve this image tracking by placing radiopaque marker bands at specific locations along the surface of the catheter. This enables us to discern rotation along the backbone, as shown in simulation and from fluoroscopy on the right. Our estimation approach first relies on segmentation of these markers in two imaging planes, then reconstruction and finally solving the shape and pose from these estimated marker locations. A 2 mm diameter prototype was made using a tecothane catheter with tantalum markers placed along its length at measured locations. This prototype was imaged under biplane fluoroscopy in different bending configurations, with fluoroscopic images collected for each. Across 29 different configurations, the shape and backbone rotation were computed following the estimation approach. The RMS error across all estimations was reported as 1.14% of the catheter's length, indicating high shape tracking accuracy. The error of the backbone rotation was found to be on average 28 degrees, which is acceptable considering torsional transmission losses can be as high as 180 degrees. An additional 1.4 mm outer diameter prototype was made from a standard microcatheter and was inserted in a mock vertebral artery. This demonstrates intended clinical use of tracking catheters within the neurovasculature.